Okay, here's a tutorial on projectile motion. This is specifically, I put a bunch of stuff in here for the being able, a project I'm going to have you do at home. Should be fun. So, but first let me go through projectile motion in itself. Go through this Project Lead the Way PowerPoint. A few little levity here. Pause for laughter. Because once he looks down, he goes down. A little more, one more. Sometimes if you know too much, actually this guy right here, that's one of the formulas we're going to be using. So it's real stuff. But yeah, takes too long to calculate, you're in trouble. Okay. So some of the vocabulary. This is one we would have done another activity about speed and velocity, but we're just jumping right into this. But speed and velocity, I think I've talked about it. Speed is how fast you're going. And velocity, speed is a scalar quantity, which means it's just a number like 50 miles an hour. Velocity is a vector quantity, which means how fast it's going 50 miles an hour to the right or to the north or something like that. So that's the difference between those two. But what we're doing on this one is mostly about acceleration. Acceleration is where you are a change in velocity. You're speeding up or you're slowing down at a regular speed over a certain amount of time. Okay? And we're going to be talking about the acceleration due to gravity. That's the thing that we're going to be working with. Gravity, it's what pulls everything down towards the center of the earth. It is a constant. It is a number. In the metric system, it's 9.8 meters per second squared. In our system, negative 32. Negative because it's pulling down. It's going down. Down is a negative number. So 32 feet per second squared. 32 feet per second. And I'll explain what that means as we go through this PowerPoint. So we've got this guy. Skydiving, usually you don't just sit on the wing and fall off, but that's what we're doing. So at the beginning, he's staying flying across, but we have our acceleration up here again, 32 feet per second. So after 1 second, his velocity is 32 feet per second because he's accelerating at 32 feet per second. So that's what's happening. So after 2 seconds, 64. 32 the first second, 32 the second second. After 3 seconds, how long will it be? That's right, 96 feet per second. Okay, so it just keeps increasing. 128, 160, 192. Okay, wait, let's back up one. Now, would he accelerate forever? I think most of you understand he wouldn't. There's some point where the air pushing against him, the force pushing against him with the air, it's what's called terminal velocity, meaning you can't fall any faster than that. That the force of the air pushing up balances out the pull of gravity pulling down, and so you stay at that constant speed. And I don't, it changes depending on what it is. You know, a ping pong ball would have a very low terminal velocity. You know, it's not going to go that fast. But a rock will have a greater one because it's got more mass. So it is different, but just wanted to throw that in there so you understand he's not going to accelerate all the way until he hits the ground. Now, what's more daring than skydiving? It is the human cannonball. Ooh, sound effects. Human cannonball. So this same guy in the same position climbs inside of a cannon, and he will be a projectile. Basically, it's a moving object. Only active force is gravity. So when we launch him, here's our variables. We have Greek letter theta. That is our angle. That's our firing angle. And we have our v sub I, the initial velocity. That's the speed, the instant right when he leaves there, that's his initial velocity. And then as he goes up, gravity will pull against him and he will slow down. So that's the fastest he's going upward is right when he leaves. Okay? And so we got that. So if we shoot him straight up, theta equals 90 degrees. Obviously he starts out at 128 feet per second, decreases by 32 feet per second every second. After 4 seconds, he's at the top. Then he comes back down, speeding up, accelerating. They did sometimes they've done tests like that. You know, if you fire a bullet up in the air, it does come back down and it is moving fast. Not as fast as when it left the gun. They've done tests and it tumbles. So it doesn't come down and have that same ballistic thing, but people get killed. I've had students tell me the bullet came through the screen of a pool one time at their house from somebody firing from a long ways away. So you don't want to do that. Don't try this at home, yes. Now, if I fire him straight at the target, will he hit the target? No. He will fall down because gravity's pulling him down. This is a parabola shape. So after 1 second, he's still coming down. This is the 32 feet per second thing as he's coming down, as he's pulled down. So that's why, and all you guys that do all your games firing all this stuff, you can't shoot straight at somebody unless you adjust your sights. But if you shoot straight at him, you won't hit him. Which brings us to our formula. We're going to see it in 3 versions, but it's the same formula. To calculate how fast this is, square root negative acceleration due to gravity times the distance that he traveled divided by the sine of 2 times the angle. Now, this is a negative g because g is a negative number. So I'm going to say this several times. So when you do these calculations, and you will, this is actually going to be a positive 32 because it's a negative 32. Just please remember that, because you try to square root a negative number and nobody's happy. Okay? So that one would tell me the initial velocity. I rearrange it. Okay? I square both sides and do all that. Now I can find out how far. So once I've calculated my initial velocity, I can now figure out how far it's going to go for any angle. Once I know this, I put in my angle and it will tell me how far it's going to go. What angle do you think will he travel the farthest at, between 0 and 90 degrees? What angle should give you the largest x? 45 degrees, halfway. At 45 degrees, you should get the greatest distance. And finally, we recalculate it. I had sine of theta, so sine of 2 theta, so I take the inverse sine. So this is the exact same formula we just saw. It's just rearranged, so I can take that same formula and I can find the initial velocity. I can find how far it's going to go. Or once I know my initial velocity, if I want to know how far I want it to go, I want to hit a target, this formula will tell me what angle to launch from. Okay? So that's the basic information of this formula. So you get problems that look like this. And I'm going to do this. I'm going to see if this will work for me. I have to go to here. I'm going to try to draw on here. Let's see if this works. So just to solve one problem with you. Put this here. I've got my little stylus. So here's my formula. And so I'm going to plug in the numbers that's in this word problem. 30-degree angle, 20 feet. So 30 degrees is my theta. And 20 feet is my what? My x. That's how far it's going to go. So v sub I equals square root of negative, I'm going to put it in there, but it's a negative 32 times my x, which is 20 feet, all over sine, okay, 2 times theta. I'm not going to do it in the parentheses, 2 times 30, so it's going to be the sine of 60 degrees, okay? And so if I bring up my calculator, we'll do it right here. So I can do 32 times 20, 640, and then I want to divide by I think this works, 60 trig sine equals, that's a big number, and now I need to click second here, and that'll give me my square root. And so that's my number. V sub I equals, what was that, folks? That was 27.2. Okay? 27.2. And what are the units for that? Velocity. So feet, doesn't want to write for me, per second. Okay? feet per second. Okay, let me turn off that pen thing so that doesn't happen anymore. And we'll go back to the PowerPoint. Okay, so I've actually got that. I'm going to put these later slides in the Canvas thing, and I have that work there so you can use it as a reference. Remember, negative, negative. All right, so here's what you're going to do. You're going to build a projectile launcher. How cool is that? Now it can be something very simple, like this guy, this one right here. All this is a rubber band shooting a bottle cap on a book cover. And this works good because I can get my angles, because what you want to do is you're going to launch it at different angles and gather data. Here's one where they did some kind of a thing, a rubber band made a launcher. This one, I don't have a video of this one, but basically he's got a stick in here with a bungee cord, and he has a tennis ball in here. And again, the important thing is that you can change these angles. This one, I know some of you recognize it. This is using air pressure. They're pumping it up. Got a ball thing here. Now, so basically, I'm saying you can use a very simple design like this, any size rubber band or whatever. You can attach it however. I'm trying to make it so that I think everybody can make something. If you have a rubber band in your house, you can make this. So I think everybody, don't use, let me say this a couple times, don't make a catapult. The problem with catapults is that we want to be able to launch from different angles, and catapults are very difficult to do that with. So try to stay away from a catapult. Let me say it again, don't do a catapult. All right, do something else, but you can do that. If you do something like that, please be careful. But I know some of you might want to do that. Because this is what's important. I got it here. Look, be careful. I take no responsibility. Compressed air, or there should be no flammables. I take no responsibility for that. I'm leaning towards the rubber band. Okay. The important thing is you can change the angle of the launcher to record the distances, and use a protractor to make those angles. And if you're using a rubber band, make sure you pull it back the same distance, eliminate any extra variables. So, what do I do with this? How do I do all this, you may ask? Let me show you. All right, here's what you're going to do. So you're going to build your projectile launcher. There is a Word document on Canvas that you download that has these charts in there. Just these are empty. So what you do is once you've built it, you use a protractor. Now, what I did, I got some pictures down here to show you what I did. I Googled protractor. If you don't have one at home, don't say you can't make it. I Googled it, put it up on my screen. This one, I put a piece of paper over the top of my screen, and I drew the lines where those angles were, and now I've got a little homemade protractor. So you can do this, okay? Because you need to be accurate with your angles, okay? And so you would put that next to it as you adjust the angle. So you're going to go through these different angles. At the beginning, you're going to start at 30 degrees, and you're going to launch it 10 times. It won't go the same distance every time. You record all those different distances. Depending on what kind of thing you're doing, if you're doing a bottle cap, it could be in inches. If you're doing a tennis ball with a bungee cord, it might be in feet. If you're doing something bigger than that, I don't know, but you got to make sure it's something you can measure the distance. Because if you just show me something that launches thing 100 yards, cool, but you can't measure that. So make sure it's something you can get the measurements off of, okay? So you do that first. Then you take this average right here and you plug it into this formula right here. That will give you your initial velocity, okay? Then you take that initial velocity and you plug that into the other one. You plug that into this one. I'm jumping around. You plug it into here. Now I know my initial velocity. You plug it into here at 10, 20, 30, 40, 50, 60, 70, 80, 90 degrees to get different X's, okay? And you record that on, I don't have that here. Oh yeah, I do right here. That's this right here. Here's my different angles, and that's how far it went. Now this will be an ideal. This is not something you do yet. So this is with the calculator. All of this is with the calculator, and it's explained in the Word document. This is with the calculator. This is the ideal distances it should go. Then you actually do it, okay? Then you actually do it and do it a couple of times so that you can do an average of how far it actually went. Once you have that initial velocity, you can find the ideal distance it should go at 60 degrees, and then you launch it from 60 degrees and see if it actually does. So you'll have two columns of data, the ideal distance and an average of the actual distances. I would do it at least twice, maybe 3 times. You got plenty of time. What else you got to do, right? Oh, here's the other one right here. So there's my other formula. I use that one to do this thing right here to find the distance, v squared sine 2 theta over g, because I'll know that then. All right? Then, once you have that data, you are going to make a spreadsheet. Okay? Here's my ideal range. This is calculator only. This is calculator numbers. And then these are actual numbers. Okay? So these are actual numbers of what you actually got. And then you take that one. You can really, I did all 4 lines here, but you can do this column and the average just to do a comparison to see how well you did. There is a video on Canvas showing how to make this spreadsheet and how to insert your data in there. Pretty sure this will all work with Office 365 Excel. I sure hope so. If not, we'll figure that out later. So you do all of that. Then what you turn into me on Canvas is a PowerPoint with a picture of whatever you made, a screenshot of this right here, and then a slide that summarizes stuff. Tell me how it went. I want you to tell me, because I'm not there to watch it. So I really want to, if you want to attach a video somehow or do something else, that would be, however you want to do it. But I want to hear how it went. So tell me what went really well. Tell me what problems you had, and if you're going to do it again. This is a great project. You can do this as a family thing if you want to. It's something to do where you can get everybody there. If you got a little brother or sister, they can go catch the ball for you and help you measure it. And while it may seem like a simple project to somebody, when you show them the formulas, the fact that you're doing this kind of stuff here to calculate things, and you're making a spreadsheet and drawing this graph, then they realize, okay, yeah, this is at a higher level than just somebody shooting thing to see how far it goes. So this is the assignment. Now, if this could be a lot for you to do in a week, and I understand that. So I'm going to put a due date on Canvas for 1 week, but I have no problem taking this the second week. I'm going to put some other stuff up. Basically, after this is done, I've got one more project. We're going to do some online robotics programming. They've got a new software program out there, and we'll work on that pretty much for the rest of the quarter. So, and I'll put that out. But I just think this would be fun. There's an online one that does Projectile, a little program that does it. But I thought this is something everybody can do, a little hands-on project. So I think you're going to like it. So let me know if there's any problems. Email me, Teams discussion on Canvas, whatever. But have fun with this. Oh, I have one more line there. Yep, have fun with this, and I think you're going to have a good time. All right, thanks.